Hey guys, welcome back. Today we are going into Unit 7, which is all about forces and motion. So Unit 6 we talked about motion. Unit 7 we're going to focus a little bit more on the forces side. So we're still doing some physics concepts here. So without further ado, let's go ahead and get started. Today, our first lesson, we are going to be talking about the difference between mass and weight. So what is the difference and how do we calculate it? So first, before we talk about mass and weight, we have to talk about gravity. So gravity is going to be dependent upon the mass of two objects and the distance between them. So if mass increases, the force of gravity increases as well. So the reason that we actually are on the surface of the planet, so remember our planet is spinning around on its axis, it's also whirling through space in its revolution as it's going around the sun. The reason we don't just, fly off in every single direction is because there's an attraction between us and the Earth. So there's a gravitational pull between the planet and yourself, okay? And the force of gravity on Earth is negative 9.8 meters per second squared. So that's the force of gravity. If your distance increases, the force of gravity also decreases. So Jupiter has more mass than Earth, therefore it would have a stronger gravitational pull. And in this example, we have a little person standing on Earth, and then we have the satellite that's further out along with the little astronaut. So the force of gravity is going to be stronger on the person on the face of the planet because they're closer together. So the force of attraction is greater. For the satellite that's up in orbit, the force of attraction isn't as great because the satellite is further away. So now we talk about our weight. You guys know about weight, right? You probably go to the doctor to get checkups, and one of the first things they do is ask you to stand on the scale so they can measure how much you weigh. So weight is just a measurement of how strongly gravity pulls on a mass. So when they measure your weight, they're basically measuring the force of gravity that's working on you on the planet. So it's completely dependent on the amount of gravity there is. And it's the result of the force of gravity. So without gravity, there would be no weight. That's why people are weightless in space. Without gravity, you would just float and you would have no weight. Okay. So the amount of mass and gravity is going to equal your weight. So if you add more mass, which is just how much of something there is, then you increase the attractive force between you and the Earth. That's why some people weigh more than others. If a person has more mass, they're going to weigh more. So if mass increases, the force of gravity also increases. If you leave the Earth and you head to outer space, you're further away from the gravity source, therefore you weigh less. Okay, so if distance increases, the force of gravity decreases. So here we have our little astronaut. He's spinning around in outer space. He is weightless because there's no force of gravity working on him because he's so far away from the planet. Okay? Now, mass and weight are not the same thing. That astronaut that's floating around in outer space, he still has mass, right? He didn't just disappear into nothing. He's still an object. He still has mass. But there's no force of gravity, so he is weightless. Okay, so we got to make sure we know the two things are not the same. So mass is the amount of matter an object contains. It has inertia, aka a resistance to a push or a pull, and we'll talk about inertia a little bit more later on this week. And then the weight or the force is dependent upon gravity. The mass is not. So mass is independent of gravity. So your mass doesn't change. Okay, the amount of stuff that makes you up as a person, that doesn't change, unless you lose fat or something like that. But in the context of just talking about the difference of being on the surface of the planet versus being an astronaut in outer space, the amount of stuff that makes you up as an individual, that stays the same, but your weight is dependent on the force of gravity. Okay, which is just that attraction between two objects. And it can change if the objects change distance or mass. So if you did, lose fat, go on a diet, or gain fat, you could change your weight because it's dependent on how much mass you have. Okay? So mass and gravity together equals your weight. Okay, so smaller mass, less pull, so less attraction, less weight, and the opposite is true. So the more mass you have, the more you weigh because there's more of an attraction and more of a pull between you and the planet. Okay? So weight is really just a measurement of the gravitational attraction between you and the Earth. Okay? Weight is a force measurement, so we can actually calculate it. Okay? So let's just compare really quickly on different planets and let's see how gravity can affect our weight. So let's pretend we're a person on Earth and we weigh 150 pounds. So that's like average for a human adult. Okay? The same person that weighs 150 pounds on Earth would weigh 354.6 pounds on Jupiter. Why? Because Jupiter has more mass than the Earth. Therefore, the gravitational pull between you and Jupiter would be more intense and you would weigh more. It would be extremely hard to move yourself around on Jupiter because you would feel like you just weighed so heavy because there's such an attraction between you and the planet. Okay? Now, your mass doesn't change. All right? Between this trip between Earth and Jupiter, you're still made up of the same amount of stuff. You haven't lost or put on any kind of fat or anything like that. But you land on the planet, and even though your mass is the same, your weight has over doubled, okay? So how does gravity play a role in an object's acceleration? So how objects fall as a result of gravity was a matter of debate for scientific thinkers as far back as ancient times. So why were things falling? Remember the classic Isaac Newton sitting under the tree and an apple falls and hits him in the head and he kind of has this like scientific revelation, right? So Aristotle felt that heavier objects with a greater weight would fall faster than lighter objects when pulled by gravity. And this was pretty much accepted for hundreds of years, right? The more you weigh, the faster that you'll fall. And after many years, especially during the Renaissance, a scientist named Galileo had different ideas. He felt that all objects would fall at the same rate, no matter the mass or the weight. And so, as scientists do, he sets off to prove his theory. So he took cannonballs to the top of the Leaning Tower of Pisa, which is this one that's leaning because of substance in the ground, but that's a different story for earth science. So he took the cannonballs up to the tower and he threw them off the edge. And what happened? Well, let's see. So, again, up until this point, the idea was that if you threw two objects off a tower, the heavier one would fall faster. However, Galileo found that no matter how large or small, the objects fell at the same velocity, right? Remember, velocity is your displacement over time. So, at what rate do objects accelerate due to Earth's gravity? Well, basically, through this experiment, he found that the acceleration rate on the Earth, aka the force of gravity, is the same for all objects, okay? And he found that this value was 9.8 meters per second, okay? So the acceleration rate of the Earth, or acceleration due to gravity, is 9.8 meters per second squared. That's how fast your acceleration would be if you were to, jump off a building, or you would throw something off the building. Okay, so gravity's acceleration on the Earth is 9.8 meters per second squared. Okay, now if we want to solve for weight, there's a formula we need to know. And that is force in newtons is equal to your mass in kilograms times acceleration rate due to gravity. Okay, so newtons is just a unit. It's a force unit, so we're going to have to get used to that because we're going to see that a lot in this unit. So force in newtons is equal to mass in kilograms times your acceleration rate of gravity. The acceleration rate of gravity will be the same on Earth for every single problem. It's 9.8 meters per second squared. Okay? Now, if you have a problem where you're on the moon or on Jupiter or something like that, the problem will have to tell you the gravity. But if you're on Earth, we're just always assuming that the acceleration rate of gravity is 9.8 meters per second squared. Okay, force is equal to mass times acceleration, where acceleration is the force of gravity, which is 9.8 meters per second squared. Okay. Okay, so that means your weight, which is the force, is equal to your mass times your gravity acceleration. Okay. So that is the biggest takeaways for today. So we have to know this equation. Force is equal to mass times acceleration. We have to know the acceleration due to gravity on Earth is 9.8 meters per second squared, and we need to know the difference between mass and weight. So weight is the measure of the gravitational pull, depending on what planet you're on. Hopefully we're all on planet Earth. And then mass is just that measure of how many particles makes up the object. Okay, we're going to do some practice with this in your independent practice today. Of course, I'll have some more example videos, but this is the end of your notes for your first lesson of this unit.